Oh,
Mike.
actually, wait a second.
All right. There we go.
All right. My name is Jeremiah Rounds. So yesterday, Dr. Cleveland described some work on a data set, and today I've been asked to talk to you through some of the technical details of how that work was accomplished. And I've got our little plot up here, and I describe it as voice over IP data flow. And I probably should be careful with that word a little bit. I picked it up from watching sort of enterprise level presentations on Hadoop. And for us, it's probably not the same meaning. Here I'm just describing how we end up from some log files ultimately to some near exact replicates, which you'll hear about in the course of the day, maybe even tomorrow, and then some detailed analysis. And there's kind of an unbroken string of operations that have to happen to get there. And that does not necessarily mean that's what happened when they were analyzing the data. As you can well imagine, whenever you analyze any data, you have many missteps and many iterative operations and many reconsiderations of what you did. And part of the reason we like RIPE is that it lets you do those sorts of exploratory steps quickly, so you're not in a tremendous commitment as far as time. I'm going to describe the MapReduce operations that were necessary to create a bunch of data sets. But at some point, you're going to realize that the MapReduce operations I'm describing are essentially just functions applied to subsets of data. There might be one case where it gets more exotic than that. And at that point, I've done my job, because that's what we like about MapReduce. We like that idea. Because it lets us simply distribute some computation over subsets. It just comes down to that. OK, so schematic. The story begins with log files. Everybody's data analysis usually starts with log files. Somebody gives you a bunch of text files, in this case zipped up, and you need to do something with them. The first thing we do is we use a put command to put them on the HDFS. And at this point, they really don't have a key or a value. They're still text files on the HDFS. And then there's this first MapReduce. And at that point, they really take on some key values. And the keys come from a reader that it comes from Hadoop, which is just one of several default readers. Reads the text files, and its keys are byte offset, and the value is text line from the file. And you can also learn the file name if you need to. And that will, through that MapReduce, will create a data set that we call the semi-call basis division. And in that data set will be a key that's semi-call conditioning variables. So all the variables necessary to describe one unique semi-call. And then the values will be a data frame, an R data frame, with arrival time and a flag that comes from the packet. And this will be from parsing the text file. And let's go ahead and see that. So what I'm trying to create, here's the put operation. The voice over IP call logs, there's 1.315 billion packets over 332 calls. Spread out over 48 hours over 2 days. Each hour gets a zip file, and depending on which direction it was coming to where we were recording them, it was in or out. Unzipped, you basically get an arrival time. This is your text line. You get a bunch of stuff that we discard. You get a source IP, a source port, a destination IP, a destination port, and a flag that describes whether or not the packet was a voice packet or something else. And so we can get these on the HDFS through this command that we wrote called rhput. You can also use Hadoop DFS-put. And here I'm describing my cluster directory, my center for computing directory, my Linux login basically. And here I'm describing the HDFS directory I want it to go to. And so that all happens from inside R. And now I'm creating the semi-call basis division. And what we want to do is we want to move from the text files to something that looks like this. Here, I'm giving you output that was recorded from inside R. I've copied and pasted from inside R. And this comes from a command that we wrote called rhread that reads all the key values associated with a particular directory on the HDFS. And you can see what the keys look like when we're done. You get a source IP, a source port, a destination IP, a destination port. This is a one-line data frame. And I chose DataFrame simply because it's the easiest thing to work with in R. A prior incarnation of this work, they chose a string where they put quotes around this and strung it all together with dots. And then they had to reparse it every time they worked with it. And I didn't like that idea. And the values we're going to get out are these times, arrival times, and a true or false describing if it was a voice packet. And we'll get this for every single semi-call. So here's what the map and reduce look like. So this is not pseudocode. This is what I type in R. You can cut and paste this in R and it works. I say map equals expression. Expression is kind of a weird data type if you've worked with R. So who's worked with R? I know I saw some hands yesterday. Yes? Who's worked with the expressions? Exactly, me too. Never worked with expressions before I worked with RIPE. An expression is just a vector of unevaluated code. So when we put this expression keyword around things, we're saying don't evaluate this code, just make some sort of object that references all these operations. So we got unevaluated code in our R instance. We say for v in map values, string split the v because remember it's a text line. We're stripping it, or we're splitting it by all the white space, and then it comes back as a list, and we don't want that. And the key will be just the split string cast to numerics or strings depending on what it is. So the fifth spot was source IP. The sixth spot was source port. The seventh spot was destination IP. Destination port was a spot. I'm making the key a data frame because it's easy to work with. And then I made the value a tuple. The first spot was the time, and the ninth spot was that flag. And then I say rhcollect key value. So I'm doing this for all the map values, which is all the lines in the files. That happens, and now I write my reduce. My reduce again is an expression, and now the vector really comes into play. So I have a vector of named spots, and the first spot is pre, the second spot is reduce, and the third spot is post. All unevaluated code. And what I want to do here is I want to collect up all the values for a key and put them into a data frame. So I make a data list. I append to the list the current reduce values in the reduce step. And then when I've seen it all in the post, I rbind it, which means put all those, I rbind the data, which means put all those tuples in the rows. And then I give it column names. I do a little reordering by arrival. Basically, I sort the data set by arrival. And then I cast it to a data frame. And then I do a little work with the flag. Originally, it's numeric. It's values like 0, 19, 8, that sort of thing. But 0 and 8 refer to voice. And so right here, I'm taking this numeric flag, and I'm converting it into a Boolean true-false. Was it a voice packet? And then having all that data, which is now a data frame, I send out the same reduce key to the collector, and I send out my data as a data frame. And that's it. Are there any questions? Yes?
So what's happening in that reduce? That's a recursive call there?
Which?
That one you're pointing at right there.
Oh, OK. So I have this habit of keeping track of when names are different just implicitly and naming things the same thing. Here I'm naming something in my local R instance of reduce, and it's a vector expression. And here, one spot inside that vector expression is named reduce. So two different reduces.
And how about that third reduce in the data equals in that assignment, data equals append, yeah, that one.
This guy, reduce values?
What does that correspond to?
OK, so have you used R?
Yeah, limited.
OK. So maybe I should talk about some of the peculiarities of R. Dot in C and Java means
Oh, I'm sorry, that's a dot and a comma.
a dot and comma.
The reduced dot value, not a comma. Okay. Is that right?
Reduce dot. It's just a name. It's an identifier.
Yeah, I got it. I thought it was a comma. Sorry.
Oh, okay, cool. So for everyone else not following the conversation, a dot can be a letter in R. In C, it's reserved for structures. In R, it can be a letter. It can be part of your variable name. So what happens to these? I've written them, no work's happened yet. And then I call the function that I described before, which is the HMMR, which is the thing from RIPE that constructs the MapReduce job. I tell it map, I tell it reduce, I tell it the input folder, which I've just made a constant here. I tell it the output folder. I tell it what type of data we're handling, which we're handling text files, and we're going to send them to a map. I tell it the name of my job, and then that return comes back, and I execute it with RHX. And at this point, a MapReduce job kicks off on the cluster. I don't write these lines again in my presentation because this never changes. This story never changes. You send your arguments to RIPE's MapReduce functions, and you execute them. The story is back here in how you're writing your map expressions and how you're writing your reduce expressions. So Dr. Cleveland wanted me to try to convey how difficult this was to do by hand, because before RIPE, they actually tried it. So there's two ways you could do this by hand with the log files. Forget about Hadoop, forget about MapReduce. Think about how you would get all of these semicall identifiers, all these conditioning variables that uniquely identify one semicall, and get all of their values together and get them sorted. You could do two algorithms that I can think of. The first is an online algorithm, where you basically pretend that you're seeing the data as it comes in, and you try to identify when a call starts and when a call stops. They tried that way. It doesn't make as much sense in retrospect. Going in, that made sense because you can kind of forget about calls after a period of a timeout, but you have to tune your timeout, and it adds that sort of how are you getting this timeout. And then the other part of it is you could do it offline, and in the offline fashion, you might make a hash table. You make some sort of key where you're getting all these packets together, and then you're packaging them up. But whenever I think about that, I ultimately end up deciding it's just MapReduce in another form. So why are you recreating the wheel? And here we're not. We're taking advantage of Hadoop's real power. Are there any questions? Oh, there we go. All right, so where are we? Back on my picture. Oh, I didn't give you this picture. You don't need it now. All I was describing here was the lines that come in from the files. You parse the text line in the map. You assemble the semicall key and associated line values with that key. Between the map and the reduce, the values for every line are separate. In the reduce, we collect them up, and we take all these separate values and make them into a data frame. So that gets us here in my little chart. We've gone from the log files, we've done a MapReduce, and now we're in the semicall basis division. So what else can we do? So he described a voice transmission division where we calculate some jitter. He described this jitter kind of in detail. We get there with another MapReduce on that last data set that we created. So the values of the key value pairs are these sequences of times. And a jitter is the difference between the times minus 20 milliseconds. And what we mean by transmission interval is a contiguous block of voice-to-voice packets. So you can view a semicall after it's been put together as packets like this, where an S refers to a silent suppression packet, and a V refers to a voice packet. So when they're contiguous, this is transmission 1, And when they're broken, you get another transmission, you get another transmission. So the code I'm going to describe to do this is a little convoluted. And the reason is because of vectorized operations. If you do this in a loop, it's really simple to understand. But unfortunately, in R and Python, the loops are slow. So you can well imagine, how would I break this up into transmissions? You could start at one end. You go for I equals 0 or I equals 1, depending on how you're indexing. You go, is it a voice? If it's not a voice, then keep going. If it's a voice, start my transmission incrementer. So I've got a transmission incrementer and go, well, all right, increment the transmission incrementer and associate that value with the voice. And then when it's not changing, was the last value a voice, or you're in a loop, you just keep the same number for the transmission. And then when you leave that transmission, you set some flag, and then you get to the next transmission, you increment your transmission counter, and you could do that algorithm in a loop very easily. And then it would be slow in R. So it looks a little different when we get to it. Here's my picture. Semicall. Semicalls are identified with source IP, source port, destination IP, destination port. Those are the keys. And we constructed a data frame last time of arrival and voice. This should say semicall 2, so I'm indicating there's more than one call. They go into the map. We identify the transmission as continuous voice-to-voice packets. We calculate jitter for each packet. And then we change the key. So between here and here, we're going to append our transmission number to the key to separate out these transmission intervals. And then when they hit the reduce, they'll be separate. And we can just do what's called an identity reduce, which is just output whatever came out of the map onto the data frame. Yes?
Are silences treated as transmission? How are those stripped out?
Those are stripped out. So when we say transmission, we mean voice-to-voice packets. So here's the convoluted part. So the map begins like every map begins. For I in sequence along map values, which is basically a for each map value. K equals map value keys, and V equals V equals map values I.
So that outer loop, is that optimized, or is that slow R looping?
It's optimized. It's not optimized, but there's no way around it at this point. So I mean, I actually stripped out an lapply, if you're familiar with R and lapply, because I don't think it would run any faster. Basically, a list apply. They ran a list apply along sequence of values, but at that point, if you're running a list apply along the sequences of the indexes, you're just doing a loop. But yes, it could be better if we conceptualize this a little better. In fact, after I had this conversation, I was trying to think of a way to vectorize the map value operations, but get them in such a way that you could just hand a list to some version of RHcollect, and it would stay vectorized, and you would never have to loop over it. And that would be nice. One of the things probably holding us back there is there's no concept of a zip operation in R. So in Python, you can zip two lists together. And that's really nice, because that's basically what we're doing. We have map keys and map values. What we want to do is we want to zip them together and then go along the pair. And you can do that elegantly in Python, and R not so much. OK. So we need to know the number of packets in the transmission, and if it has less than 2 packets, we're done with this value, because there's no intervals that we're interested in. So here's the part where it gets a little convoluted, where a for loop would be so clear, and this isn't so much because it's faster and vectorized. We got V $voice, which means the voice column of our values, -1, which means drop the first value. And then we're ending it, where this is a logical end, V $voice minus number of packets. So we're getting rid of the last value. And so what they've done there is they now compared 2 vectors to see if they're voice-to-voice, but they've shifted one down and shifted one up. Or, you know, I thought this through on paper once, and it works out clearly. It's just a little confusing to say. But basically, if they're sequentially voice packets true and true, they'll end up true here. So this becomes a voice-to-voice vector. If the sum of the voice-to-voice is 0, then you have no voice-to-voice transmissions in your call. So next, you're done. There's nothing interesting there. And then we begin the jitter calculation. So we describe the jitter. We get our arrival times. We just take it out. The jitter is the difference between the arrival times. So difference is a function that goes along each value in a vector and calculates literally the difference. But we're only interested in the jitters of the voice-to-voice packets. So we go ahead and subset it. And one of the reasons we reduce the size of voice-to-voice, the logic of it, is because difference is 1 less than the length of arrival. So we round jitter, and then we multiply it by 1,000 to put it in milliseconds because it's in seconds. And then we record the arrival times that are important, which is the voice-to-voice arrival times. And then here we're back to some logic that's been vectorized that would, again, be clear in a for loop very easily, but now is a little confusing, which is where we want to know where the transmission intervals start and stop. And to do that, they appended false to the front of the voice-to-voice, true, false, and to the end, and then they did a difference. And what that gives you is 3 values in the resulting vector. You get a 1, you get a 0, you get a -1. And it's 1 if you've started a transmission, it's 0 if nothing's changed, and it's -1 if you've stopped a transmission. It's just a bit of cleverness. This is something I would not have thought up. So this code wasn't mine. I just cleaned it up for presentation. And I wonder to myself if I would have thought of this, and I probably wouldn't have. And then you just need to figure out where voice transmissions start and where they end. You just need to ask yourself, where is this vector 1 and where is this vector -1, which is what which does. And now we're actually constructing our output, which is, oh, by the way, if you have no transmission intervals, we go ahead and kick out with the next and say we're done. Done, finished, we don't want to omit anything here. So now we're constructing our keys and our values. Our data is a data frame of the arrival times and the jitter times. And I've put it as a matrix because some downstream operation, I thought that would be faster. It's easy to cast from or to matrices and data frames where you're dealing with numerics. And now we are to subset our data frame. So the number of transmission is the length of start voice at this point. And then the transmission length is the end voice minus the start voice. So both of these are vectors. They're vectorized. They describe the start of a transmission and the end of a transmission. So you subtract them and you get a length. And this, too, is a vector. It's a vector of lengths. And so we can repeat the identifier for the transmission by the transmission length. Repeat has this operation where it understands a vector of how many things to repeat it by. So it doesn't always have to repeat by the same amount. But it replaces these indexes, repeats these indexes by whatever's in here. So for each t in the transmissions, we can append something to the key. And this is why I like working with keys as data frames. So we have this key that comes all the way up here from map keys. If we want to add something to the key to make it more expressive, to add another conditioning variable, we go key $ transmission equals t, and now it's part of the key. Now we've got transmission in the key. And then we say the new value is the subset of our data where transmission equals t. So vectorized subsetting, and then we collect it, we emit it out, and we go back to the top of our loop. Any questions? Yes?
Can you describe again what RH collect is doing?
OK, RH collect. So in the MapReduce algorithm, I described it in pseudocode as a function, right? You have a map function, you have a reduce function. We can't do that in R because the overhead of calling functions is slow. So it was made, the decision was made early on in the implementation of how we MapReduce to RIPE to get rid of any function calls at that level and just provide a list that's going to exist in memory. So that map keys and map values is coming from something in memory from RIPE, and it gets it from Hadoop. But we need to communicate basically what would be a return from the map functions and the reduce functions. And the way we communicate that is with this function called RHCollect. So you could think of that as a return from map and a return from reduce. We call it multiple times, though, so it's not quite a return. Basically, you keep calling it, you keep calling it, keep calling it, and what RIPE does is it remembers and makes a list of what you told it for each call. And then after your map code's done, whatever you've assembled is essentially your output of your list that goes to intermediate storage. Yes?
So it's basically like an append. Appending.
Yeah, it's not done in R, though. It's done back in Java, actually. Basically, it kicks out. It might even be C. There's some servers in between. It's rather complicated. Communicating between Java and R is not the most straightforward operation. So there's, this should be commented out. There's reduced code here because they had written it originally in a way that would make a bunch of different, they would need it. But I realized when I was cleaning this up and I was cleaning out some double loops that they had missed an opportunity to do a subset operation. And so that's why we don't need a reducer. We don't need to collect all the transmissions for one semicall. We can get them right away out of the map. And so this is what it looks like when you're done. The only difference between the last key value pair that I showed you, so we're back in local R, and I'm investigating the data. And by the way, loading these is how I debug these routines. So I load a little, we've got a function called rhread. And rhread goes out to the HDFS and reads a directory, and you can tell it how many you want to read. I often say like 10 values. And then I get them like this, and I play with them until my code's right. But the keys is the same as before. You've got all your semicall conditioning variables, but now we've added a transmission ID. So now it's a transmission key. And the values are arrival and jitter. So you get your arrival times and your jitter times, which Dr. Cleveland described yesterday. So the robust regression. Dr. Cleveland described this cycle in jitter. This plot, I don't necessarily think does entire justice to the nature of the cycle. So there's a cycle of every 9 packets, you get a peak and you get a minimum, and except in the case of extreme network noise, that's rock solid. It doesn't change phase on you. It's not 10 9 packets and then 10 packets and sometimes out of phase, so it's 12 packets. No, it's 9 packets. It's a little hard to see that from there, but what you can do is you can overlay calls, or you can view a bunch of them, and you can blow it up, and you realize it's every 9 packets, and it doesn't waver. So they decided what they want to do is they basically want to do just to take out this effect, because they don't think it's coming from the network, and they want to study the network. And that's where we are now. So we're just now leaving the voice transmission division, where the keys were transmission conditioning variables, and the values were arrival times and jitter. And we're going to do a robust regression and a MapReduce. So this one here means connect. So I'm connecting these to there. And the MapReduce is going to transform this voice transmission division into the same division. We're not going to change the conditioning variables that form the key, but we're going to change the jitter value. I'm calling it network jitter. That's not Dr. Cleveland's phrase. I've added that because that's how I understand it. So the data frame will end up being arrival time and network jitter. But let me paint you a picture of my MapReduce. These are my keys. These are my values. They go into the map. We're going to do a robust regression. We're going to regress jitter on basically index mod 9. And that's going to describe every 9th location. And the network jitter is the residual of this robust regression. And having that, those are going to end up, these arrival times and residuals are going to end up being pushed out of the maps as values, key values, and the reduce will be identity again. So we do nothing in the reduce. This is what it looks like. So we're back in our local R again. We're defining a map expression. I is a diagonal matrix, and we create this function called bi-square, which just is our weighting function for the robust regression, which is exactly how we'd do it if we were dealing with just one call and we were in R. We'd create some sort of function like this. And then the guts of this would be exactly how we did this robust regression in R locally, except for now we're going out there and we're doing it for every key value pair. So again, for I in sequence along map values, I get my KV, so I handle these calls as they occur. They've decided if the number of packets is less than 90, they're not interested in the call. That's just the decision they made. And then I do my indexing to assign observations to regressions. Here, with this 0 to number of packets minus 1, this creates a list 0, 1, 2, 3, 4, 5, 6, 7. Modulo 9 plus 1 and creates our assignment. We get a row out of this diagonal matrix up here. And this code in the middle is just a robust regression logic. Nothing new there as far as MapReduce, just applying a robust regression to our key value pairs. And then down here, we got a little code to decide if this is a sane result. And the value is a data frame, arrival times, and network jitter is my residual from my robust regression. They were also interested for plotting to describe the magnitude of the difference of the coefficients. And this was to sort of arrange models when they did some plotting and have some awareness of the different coefficients that were fit. So they pinned that as an attribute to the data value. So now I didn't put this in anywhere else. They've got a data frame coming out as the value, but they've pennybacked an attribute. So an attribute in R is sort of you attach an identifier and a value for that identifier to any object you want. And it doesn't affect how it's used in the language, but you can inspect it for those attributes if you want. And then out to RH collect. And then the identity is a reduce, which means everything that hits here hits the HDFS as output. All right. I think that's as far as you wanted me to go today.
All right.
So I guess, it should be becoming clear that this is a tool for data analysis that makes it easy, because there's nothing exotic about these MapReduces. They're basically almost list applies. They're almost apply this function to these key value pairs. And that's not bad. That's good. I'll move it.
Yeah. Oops.
You can use that for now.
That's all right. I already got it out.
Oh, I forgot to ask. Are there any questions?
I have a question.
Yes.
So at this point, you're comparing a certain piece of your transmission to, I think, trying to calculate jitter. So let's say you want to compare two different sets of variables, right? So right now I've got this conditional variable, which is transmission. So let's say we want to now go through and look at some other combination of the data. I don't know what we have that. It's not something else. We'd have to go through all the way back to the beginning to run MapReduce to get things collected in the way that we want. And one of the things we talked about the other day was, you have a set of features on the data set, right? And you want to say, well, what if I look at how things change dependent on this set of features? What if I say, this feature changes dependent on these two features? Or what if I look at this one changes dependent on these two features? Right? Those would be separate MapReduce routines, like pipelines. Right?
I guess if we didn't have a good amount of forethought at the beginning, the answer to your question is yes. And there's kind of a related question, which is, if I have two sets of key value pairs on HDFS, how do I merge them? Doesn't that seem related?
Yeah.
Yeah. And those are actually sticky issues. So I presented it as very easy, but there isn't a flow. You have to sometimes back up and say that we didn't do the right things. It's sometimes very iterative. It's not a magic bullet. Maybe I overstated the magic bulletness of it. It's very nice, though. It's very nice to be able to just think just want to apply this function, and I want to distribute this work, and that's what we're using the tool for. And in the process, we realized that there's some principles by which we're creating keys, and that's where Dr. Cleveland's basically grew up. And that's where we're at now. We're definitely not done thinking about it.
I think I'll, let me actually make a comment about that question. This issue does come up about trying to take, I think I'm interpreting it correctly, what we're trying to get at, taking two different divisions and trying to do something between them. But for the most part, you're not doing that. For the most part, think of it this way. For the most part, all your energy is spent analyzing a subset. Because everything that, like with this, when we're into the mode of doing this, studying the cycle in the data, we have everything we need. When we did the modeling, the actual modeling that in the end when we're all done, that's the thing that spits packets out and looks like voice over IP. Once we did the division, that was all set up, and all the variables that we needed were right there. So, I mean, it does come up, and it can be a bit of a nuisance. And actually, you're going to see it come up one time in when I'm describing in the jitter analysis. So, in fact, in the middle of the description, I'm going to ask Jeremiah, why did we do it this way? He didn't do it. Somebody else did. So we'll troubleshoot right in the middle of the discussion. Yeah, right. All right. So, all right. I want to diverge a bit here and talk about visualization. Okay. Again, we consider this to be critical to the processes of data analysis, and we do lots of it. All right. So. Remember that the way the jitter was discovered was through a plot just like this. I mean, in fact, well, this plot you could say, except we fixed the labels and things like that for presentation. But a plot like this, and so, and the idea was that. Because we have a large amount of data, and we have, 14 million subsets, we have 14 million of these things. Okay, so this is a plot for one transmission interval. All right, now you have to understand, we're starting here. I mean, we don't know what's going on. We have no idea what's going on in data. I mean, we know all about the voice over IP technology, and there's lots of ideas. So we have, we have, shall we say, soft knowledge about lots of things. But that doesn't translate into knowing exactly how these data are going to look. So, all right, so we're throwing them up. This is one interval, and we have 14 million of them. All right? So recall that we sampled them, and we tried to sample them in a way that, or did sample them in a way that made the sample representative with respect to behaviors that we expected to see in the data. Like you expect to see that things go up as jitter goes up, we know, as the traffic rate on a link goes up. And there's more queuing on the router, therefore there's going to, and the queuing on the router causes the jitter, so as the traffic rate goes up, the queuing goes up, and therefore the jitter goes up. So that's an easy one. And we know also that source gateway is remember, source gateway, which is a between subset variable, that's an important one. We know if this is coming from Buenos Aires, we expect to see more jitter than if it's coming from, the other gateway that happens to be in Newark, because it will have gone through, fewer hops in the routing. All right, so we have those two variables, and recall what we, that are between subset variables in the sense that there's one value per subset. And here was this sample that we created. So what we said was we want to, we take the 27 gateways, and that'll give us, that's the gateway variable. And then we will take samples through time, because we know that through time the traffic rate is changing on the links, in fact, all the links on all hops, although in a fairly complex way. But we'll just spread it out over time. And at least we know what's happening on the link that we measured, which also contributes to the jitter. So the sampling was equally spaced, and that is on each gateway, 48 intervals every hour. So that means the start time of the interval, which is here, the start time of the interval was taken to be every hour. So we had 48 of these intervals for each gateway. Oops, that's the second one. There's 48 altogether, all right? And also, because we wanted to see the nature of the jitter, we didn't, there's a lot of very, very short intervals. Well, if you plot a lot of short intervals, you're not going to see too much. We want to see what the time characteristics tend to be. And by the way, another thing is that the size of the interval doesn't have anything to do with the jitter. You might say, well, hey, wait a minute, maybe the small intervals are acting differently than the large intervals. So shouldn't that be a variable? Shouldn't you have another variable that, takes intervals that have a small number of jitter values to see if they're different from the ones with large number? And the answer is pretty much no, because it's not coming from anything that has to do with the call itself. It's the action, it's the action of the network itself. So, the short interval meant that there was just a short burst of transmission from the sources, not because anything on the network, but the jitters coming from the network. So we don't worry about that. So we want these things to be big enough that we can actually see something. So we say, all right, we'll look at least 700 values. On the other hand, we don't want to get it too big and sort of filling up huge numbers of pages. So we picked 2,000. So actually every interval would fit on a single page in the display. Anyway, there's 48 per gateway, but there's 27 gateways. So now we have 1,296 displays. That's nothing. I mean, we think nothing of, producing, 4,000 or 5,000. Actually, not long ago, I got an email from a former student who works at Bank of America and does a lot of analysis of financial data. And I had asked him how things were going, and he told me what's going on. And then he said, and today I made 10,000 pages of trellis displays. So anyway, but here's the thing. How are you going to consume this? So we do the sampling. We do the sampling so that we can, because we obviously can't look at 14 million displays. Nevertheless, we'd like to be able to look at many as possible. So the idea is basically you have to pay some attention to the design of the displays. You can't make a display where you're going to have to sit and study it for a long period of time. Each single display itself, each transmission interval. You need to be able to extract visually the information from the display quickly and move on to the next one. And so the displays that we design and use, and actually we're able to do quite well with this, although we don't exactly have a theory of how you do this. I'd be hard pressed to say, oh, we got those data, we'll do it, do it like this, unless I'd already tried data like that for a problem like that. But nevertheless, typically if you give it, well, actually there's some displays that there's no problem at all. You can look at it for a moment if you have, and it just quickly comes out. In other cases, you have to actually attend to the design. But the idea is that as you navigate through the display, it's under the control of the user, so you go through the pages. But nevertheless, you you carry out what in effect is an animation. You go through fast enough that you call it animation, except that it's punctuated with stops. In other words, you go through and then suddenly you see something and then you think about it. Or you stop and you think. You think about what's going on. Now again, the principles of display design become important. And what has to happen is that what it is you're looking for needs to be transmitted through a gestalt, a pattern that forms effortlessly. You don't actually have to use focused, careful, focused viewing locally in the display to figure out what's going on and then sort of move around and say, oh yeah, this is there, this is there, this is there. That you just look at the display. Actually, this is what's happening here with the cycle. The pattern is very clear. Now, it is true, as Jeremiah said, if you want to know exactly what the cycle is, then it is true you have to do some counting. But as soon as you do that, you're in pretty good shape. And also, well, it's clear there's a cycle here. Now, what's its phase? Is it phase exact, or is it moving around? Actually, it gives a sense of, when you view it, that the phase is not changing. But, obviously, the display is not going to show you everything. But clearly, there's some cycle here. There isn't any question about that. And you get some sense, almost instantaneously, you get some sense of the magnitude of that cycle, the amplitude of the cycle. Because when we go here, you can see clearly the amplitude is smaller. All right, so this has to do with gestalt formation. And that was easy in this case. We just made the display. Oh, by the way, we do know something about perception that was applied here, namely it has to do with the aspect ratio of panels. Things are cut out and it's like this. Actually, this is one plot, which if you extended it end to end, it would be very, very long and not very high at all. So it has, in some sense, the plot has an extremely small aspect ratio. I mean, if you think of these end to end, it's sort of this distance divided by, the sum, this one horizontal distance divided by the sum of all these distances. But we already knew that if you want to look and be able to perceive local behaviors in a time series like this, that, and you've got a lot of them, somehow you're going to have to figure out how to make that aspect ratio very small. And so the way you do it is you sort of make it small, but then so you say, you have this virtual graph in which it's extremely small, but then you chop it in pieces and stack those pieces up. So we already knew we'd have to do that. Okay, now here's actually, is this the right order? Yeah. All right, so here's another example where actually it's a little less apparent how to do this. So what's happening? What have we got here? This is this isn't voice over IP. This is just regular old TCP transmission of files on the internet and that sort of thing, reliable transmission. So anyway, but what's happening here is that we have both directions of a connection now, and the lines, the vertical lines, are portraying the size of the packets. Okay, it's log base 2, 1 plus data bytes in the packets. The amount of data bytes, not the size of the packet, but the amount of data bytes in the packet. Okay, so they're the vertical lines. But we have two directions. Now, when you make a plot like this, what you'd like to have happen is you'd like to be able to, you want to see the interplay between the directions, locally in time. By the way, this is the sequence. This is not time. Okay, so you're sitting here and watching the packets back and forth in a single connection on a link, and they're arriving through time. Now, we're not plotting against the arrival time. We're just plotting against the arrival order. All right, so this is some connection for some application. Might be SSH, I'm not sure. But anyway, these are the packets in the two directions. Now, what you'd like to be able to do is see the interplay, but you also want to be able to see each direction as a gestalt. You want to be able to look at it and just see it, as if the other one wasn't there. And if the other one's getting in the way of, each direction is getting in the way of each other, then you're not, then it's harder. And so then you have to go, well, let's see, which one's next, and go through it and do focused viewing. Okay, so here's one way to do this. Here we didn't have, well, here we have some principles too we know about to apply, but it's tempting to do this. It works not too bad. What's different here? Interesting. Okay, here, what we've done is we've gotten rid of the color. And, but now we're drawing the two directions so that one direction, the scale is sort of up, and the other direction, the scale is down. Now, one of the disadvantages of this is that we don't get to see a comparison of the sizes of the packets as effectively as we did on the previous plot. So we've given up a little bit. And now we can do a pretty good job of differentiating the two directions. Certainly better than before. But then if you add the color to it, you do even better still, and sort of visually separating and differentiating the two directions by this mechanism. So now the packets in each direction are forming a gestalt, and you can still see issues having to do with the order of the packets. Which one is coming next, and what are the sizes like? So anyway, this is just an example of the kind of thinking that sometimes you find yourself carrying out when you expect to, when you're in a situation where you're sampling and trying to make as many displays as you possibly can from the sample. So let me show you. Actually, I'll bring this down here. It's the same size, yes. So let's take these jitter plots. We had 48 per sending site. So here they are. They're sitting in a directory. Actually, these are better when you have these. We call these visualization databases because we get an awful lot of files containing packets, and somehow you have to organize it. By the way, we haven't thought too much about this. We just, we can only do so much, and we in terms of how one, how one views and organizes our visualization databases, we just haven't gotten around to really doing some serious work on it. So we just grab tools that exist now and use them. So actually, but putting them actually on the web, using HTML or using a wiki is a good way to organize things and then be able to access them in some cases. So anyway, these are just sitting in a directory, and so here they are. Here's the 27 files of the for the 27 gateways, each with 48 displays. Now, 48 is actually a small number. I mean, we have some, when we do this, oftentimes there are cases where we have 1,000. So let's take a look at, we had been looking at Rochester. Let's take a look at Rochester. All right, unfortunately, I didn't configure this to automatically do this. Sorry about that. Anyway. Where am I? 39. Well, that's interesting. Huh. All right. So here we are. So there's 48 pages here. And just click through them. Let's go through them and see. I mean, how slow or fast do we need to go? Notice there was a change here in amplitude. So by and large, it's pretty regular as we're going through here. You see some changes in the nature of the cycle. But it's mostly an amplitude change. It's interesting when it gets like this because there's a lot of things that are very close to 0 and then they're coming up. But it is keeping, actually, it's not, sorry?
A lot of it's close to 0 and then see these bumps. It does kind of seem artificial then. Like it seems like something's making those bumps intentionally. It's mostly 0, but you've got this.
I have evidence that it is.
I guess that's what if you find really clean data, you got a really clean connection, very little jitter, but then you see these little almost forced jitters every now and then. And I can see why that would be due to expect it to have been forced.
Well, yeah, actually, yes, right. Remember that well, we're almost completely positive it's because of the gateway packetization algorithm. And it's got some sort of a round-robin procedure, with a cycle of 9. It's going and maybe, working on 9 connections all at the same time. And for some reason, again, this was something we couldn't find this out because, company wouldn't tell us. So that's right. Now, actually, there's one thing about these plots, which is that the start of the plots, we actually didn't look into this because we decided we were going to do a regression on each transmission interval separately. And then, because our goal was to try to correct and then take a look at the remainder. I'll talk about that in a second. We wanted to look at the remainder. Let's see, what time did we start? Oh, OK. I'm going to say one thing, and then we're going to take a 10-minute break because, you can only go so long. Anyway, but let me just mention that in terms of the data, on the plot, it starts when the interval starts. So as we go from one interval to the next on these plots, we're not sort of we're not preserving time in any way. I mean, there's no connect. This is just when this transmission interval started, and that has to do with the call itself. All right, it's what's happening from this end. It stops and then it starts. So that's the hosts doing things. So there's no. So we're just showing the interval. So there's no. So the peaks are not necessarily occurring in the same place across these intervals. I mean, here they're sort of in this position, and then later they're in another position. And we didn't look into this because we didn't need to. But it's definitely keeping phase throughout the whole semicall. So the peaks, if we were in fact to take the intervals of the same call, we would probably see the peaks occurring in the same place. Interesting, but not of much help to us in terms of our trying to get the correction done and be done with it, because we don't want to try to fit something to the entire semicall, because we can see that through time the amplitudes are changing. Right? So we say, all right, we'll just do one interval at a time as the way of correcting. Okay? All right. So, well, I guess I sort of got lost in another thread here. But in any case, the idea is the consumption of a fairly large number of displays when you're doing this sampling is in fact feasible and works. Now, when you get into the thousands, oftentimes you're following threads because they're sort of organized according to various variables, and you find yourself, it's almost like you're exploring them, and you don't necessarily need to look at every single page. It's like if you have it well organized using something like lattice graphics by the way, lattice, the mechanism of trellis display lends itself very, very nicely to this kind of tasking because it's sort of one panel per subset. Well, with lattice graphics, you can put many panels on a single page, or just one panel. I mean, so you have a lot of control over laying things out in trellis display. It's very convenient, and you can organize that by conditioning variables. So, so the point is that there is a thought mechanism here that enables you to take the number of displays you actually are able to look at to be a pretty big number. A number that surprised some people when they hear that we made 10,000 displays. You say, well, how the heck do you get through 10,000 displays? They are navigable. It works pretty well if you make the displays, if what you're looking for forms a gestalt, and you can see it virtually instantaneously. And furthermore, there are analysis threads where you don't actually, you find yourself not looking at every single thing that's been displayed. Because you say to yourself, you know what, I'm pretty sure I understand what's going on now. Okay, all right, let's take a break. 10 minutes, be back at, sorry, did you have a question?
Yeah, I was just going to ask,
Yeah.
one of the things you talked about very early on was making sure when we're doing all the visualizations and dividing and recombining that we don't miss anything
Right.
that's important.
Right.
Do you ever find situations where going through so many trellises you skip over something that was important, or usually if you've gone through about 3,000 to 5,000 or 2,000 or whatever, that you're probably not going to see some, and if you do, it's an anomaly.
Yeah, that's a good question. Can you miss something? Well, of course. I mean, if there's one, there's an isolated thing, out of 14 million, there's one where the Nobel Prize was, well, yeah, we're going to miss it. That's, that's life. But we're trying to get, I mean, that's the way, you face the same problem when you collect data. Right? So what we're, in some sense, what you could say is, it's like we're collecting data from the data. Okay, it's really, I mean, in fact, a lot of the stuff that we do in the divide and recombine, it's like collecting data from the data. But we have one leg up on because we actually have the data, so we can go through and, when it comes to sort of sampling things, we have variables that we can compute one per subset and look at those. So we get those numbers, and we can do a very good job of designing the sampling and looking. So one of the things you can do is, if you know that there's a kind of deviation that you're looking for, you can actually say, all right, I'm going to have something, I'm going to have some function of the within subset variables, and I compute that. It's something that will characterize a kind of behavior I'm searching for, and then you go through and you compute that, and then you look at the values, that are big. You say, if this is big, I want to see it, and then you display those. That, by the way, is a very old idea. It goes back to John Tukey and back to the 70s, where they did something called projection pursuit regression for multidimensional data. You had, this metric of, you project onto a plane, and then you say, is this interesting when I project on this plane? And you do a whole lot of, you do computations to get a whole lot of projections, and then pick the ones that are interesting. So, whoops. Okay. So there is at least some hope that if it's 1 in a million, maybe you can catch it and get the Nobel Prize after all. So, okay, 10 minutes, say 5 of.
Still have to start coffee break relatively close to 10:30.
Oh, there's a coffee break in between.
Like